Okay, it's 4 p.m. exactly. So it is my pleasure to welcome you all to this next session of the Europar 2020 conference. This particular session is a joint session. We have 4 presentations. The first 2 are from the support tools and environments topic, and the next 2 are from the high performance architectures and compilers topic. So let me just remind you that we have 20 minutes for each presentations, and that includes questions and answers. And we have Slack channels for both of these topics. And since this is a joint session, we will use 2 Slack channels. The first one for the tools and environments, the second one for the high performance architectures. So please, you can use these channels to type your questions during the presentation, and then these questions will be answered by the authors of the papers, and I will moderate the entire session. Okay, so there is no need to hesitate anymore. Let us start, please. Let's proceed with the first presentation, which is skipping non-essential instructions makes data dependence profiling faster. Okay. Let us wait for the stream to begin.
Hello everyone, it's Nicolas Morew, and today I will be giving a presentation on how skipping non-essential instructions makes data dependence profiling faster. So what are data dependencies and how do they influence parallelization? A data dependence is a situation in which one instruction in code refers to the data of a preceding instruction. They are very important for the parallelization of sequential code because they are the main obstacles. Hello everyone, it's Nicolas, Morew, and today I will be giving a presentation on how skipping non-essential instructions makes data dependence profiling fast. F of I in one iteration evaluates to the same value as g of I in another iteration. We have a situation in which the same memory location is being written and read in two different iterations of the loop. This means that there is a data dependence between those two iterations, and it makes the loop not parallelizable. For detecting data dependencies in code, there are two basic approaches to follow. With static analysis, one identifies dependencies without executing the code. This, although efficient, is often too conservative, as without runtime information, some dependencies which might never occur in practice can't be ruled out. This was the case in the previous example, where without running the program, we don't know what f of I and g of I will evaluate to. Dynamic analysis, on the other hand, overcome this conservativeness by profiling each memory access during execution and reporting dependencies as they occur. This way, it has more accurate results. However, in order to find all dependencies which might occur, many different inputs must be used. This, combined with the fact that the profiling overhead is very large, leads to very slow analysis. To address the shortcomings of both static and dynamic analysis, we implemented a type of hybrid. We know that static analysis is fast, but often too conservative, and dynamic analysis is slow but accurate. So the idea is to identify data dependencies statically wherever possible and use dynamic profiling only when necessary, thus reducing the overhead generated by dynamic analysis. So parting from the source code, we would perform the static analysis to retrieve as many static dependencies as possible. We profile only the remaining instructions for the dynamic analysis, and then we retrieve the dynamic dependencies from those. With the unified representation, we merge both the sets of static and dynamic dependencies into a complete set of hybrid dependencies. A great deal of research has been made in the field of data dependence analysis, though most of the work focuses on either static or dynamic methods. Pluto, Autopar, and Taskminer are all examples of parallelization tools which implement only static dependence analysis, whereas the Discopop project implements only dynamic profiling to find dependencies. Many fewer attempts have been made at actually combining the two methods. An example of this is a project called Discopop Plus, which combined Pluto's static analysis with Discopop's dynamic analysis to retrieve the dependencies. This method proved to be very efficient at reducing the overhead of the dynamic analysis, however, only for certain types of programs. Because Pluto can only parallelize polyhedral loops, overhead reduction is only possible in code where the program hotspots are polyhedral loops. So for programs where hotspots are somewhere else, say in recursive functions, no improvements are possible. In our research, we follow a similar approach by using hybrid analysis, though we endeavor to remove this limitation by implementing our own method of static analysis. It's also worth mentioning that, like Discopop Plus, we use Discopop as our dynamic analysis tool because of its many features and promising capabilities. So going back to our approach, we said that for the dynamic analysis we use Discopop, but how did we implement the static analysis? In the following slides, I'll explain our method with some examples. Of course, the starting point of the analysis is the source code. Here we have a function foo which takes a parameter x. It initializes y, stores y's address in a pointer p. Via that pointer it changes y's value to 4, then the address of the x parameter is passed by reference to the bar function, before returning x's value. From here we first determine which are the addresses for which we can safely and completely predict dependencies statically. We call these addresses statically predictable. To do this, we first extract all memory addresses of the function. Here we have the address of x, the address of y, and the address of the pointer p. Next, we find all addresses which are referenced in the function. We consider these as unsafe or unpredictable since during our static analysis, we don't have all required information about them to safely say that we can predict all of their data dependencies. For example, we don't know what happens to x in the bar function, because we don't perform a dependence analysis across different functions. Because we also don't perform any kind of alias analysis, we can't be sure what happens to y via the p-pointer. These limitations are to be addressed in future research, but for now, we're left with the p variable as the only statically predictable address. The next step is to retrieve the dependencies for our statically predictable addresses. We see that there is a read after write dependence since p is read on line 4 and written on line 3. Finally, we report the found dependencies and omit their instructions from profiling. Again, note that because we can't statically predict all dependencies on y and x, we will have to get their dependencies dynamically. To explain how we perform our dependence analysis, I'll use another more popular function, the recursive Fibonacci. We first retrieve the function's intermediate representation using LLVM, and in that format, we then get its control flow graph. The control flow graph for the fib function in LLVM intermediate representation looks like this. As you can see, it's somewhat complex considering how short and simple our fib function looked. To make things easier for us, and also for you, we generate a memory access control flow graph. This graph contains only the information we care about, namely the load and store instructions, and it allows us to traverse these with much more ease. We perform a traversal on this graph in order to identify the dependencies of each instruction. The traversal works as follows. First, we find the exit node of the function, which in our case is the load of the returned value. This will be the parting point for our first traversal, T1. From here, we traverse the graph backwards in a second nested traversal, T2. Each path from our T1 node to the entry of the graph will be traversed in T2. If we start with the top path, the first node on this traversal will be node 3. For each node on T2's path, we compare the address being accessed with that of the node of T1. If it's the same, then we report a dependence. Here we have a read after write dependence, because the read file address is being read in node 11 after it is written in node 3. Once the dependence is found on the path, or the entry node is reached in T2, we continue with the next path, in this case the bottom one. Again, we start with the next node preceding the T1 node, which in this case is node 10. We compare the accessed addresses to find dependencies. Here again we have a read after write dependence on read file. And once no more paths are available for the T2 traversal, we continue with the T1 traversal by performing the same steps as before, with the next nodes on the paths back to the entry. If we take the top path here, our new T1 node will be number 3. Here there is only one path back to the entry point. We traverse it and compare the access addresses to find dependencies. And since we've reached the entry node and found no dependencies on the way, and there are no remaining paths for T2, we continue with T1. Here nodes 1 and 2 access the same address, but since both are read operations, which we don't report, we continue with T2. We found a dependence, because one of the operations is a store, and we report it. The same is done for each other node on the graph, until all have been traversed to T1 and all dependencies have been found. Now that I've explained our approach, let us continue with its results. Our first goal was to ensure that the dependencies reported by our method were neither incorrect nor incomplete. To evaluate this, we compared the set of data dependencies identified by the profiler with and without prior static analysis. After doing this, we found no false positives and no false negatives being reported by our approach. This means that correctness and completeness were maintained. To evaluate the performance gains, we compared the duration of our hybrid analysis to that of Discopop's analysis, as well as that of Discopop Plus. We did this on 3 benchmark suites, Polybench, NPB, and Bots, using the Clang 8 compiler and on the described platform. Here we see the average profiling overhead time for each benchmark suite and each of the approaches. We see that on average, our approach far outperforms both Discopop and Discopop Plus in both the NPB and BOTS benchmarks. It provides only a slightly lower improvement over Discopop Plus in the Polybench benchmark suite. This is because all hotspots in this suite are polyhedral loops, which Pluto and therefore Discopop Plus can statically parallelize. To visualize this a bit better, we see here a comparison of the speedups possible by using our approach and that of Discopop Plus. We see that with our method, we were able to gain improvements of at least 38% and on average 62 in every single program. This is an improvement over Discopop Plus, which in contrast could only provide improvements in code containing polyhedral loop hotspots. This, as I mentioned before, is only the case in the Polybench benchmarks and not in the other two. In conclusion, we've combined advantages of static and dynamic analyses, and we managed to succeed at implementing a hybrid data dependence analysis, which reduces profiling overhead in virtually any type of program. We extended the Discopop profiler with our implementation and successfully tested our approach on 49 programs, reducing profiling overhead by at least 38% and on average 61%. There's still plenty of room for improvement, however. In the future, we would like to combine different methods of static analysis, for example Pluto and Autopar and our approach, to further reduce profiling overhead of the dynamic analysis. Thank you all for your attention, and please email any questions to the address on screen. We would be happy to answer them.
Hi, my name is Nicolas.
Okay. So thanks for this presentation, and now we have some time, not much, but we have some time for questions. So I don't see any questions. So please, anybody has questions, just go to the Slack channel, #TO1 tools environments. Okay. So we have the first question. Thank you for a great talk, fascinating work. Can you say something about how the dynamic dependence in 4 is linked to the loop tree? This is a question from Paul Kelly.
Thank you very much for the question. But could you somehow say the question in other words, because I don't get what is the relation between dynamic dependence and loop tree? What do you mean? So yes, exactly. So when we have a loop carry dependence, of course, we want to know which loop is carrying it. So we consider the control flow graph too. So we know which loops are creating these loop carry data dependencies. So what happens then with loops with non-affine bounds? So if we can get the data dependencies statically, then we have a static phase. We get the data dependencies statically. Otherwise, we leave the instructions that create the data dependencies to the dynamic analysis phase. So we have two phases. The first one is the static analysis, where we get the data dependencies statically. if we cannot get the data dependencies statically, then we leave it for the dynamic analysis part. So for example, with a loop with non-affine bounds, if we cannot get the data dependencies for that loop statically, then we leave it for the dynamic analysis to analyze that loop. So I'm not sure if I could answer your question.
Perhaps to add, still with our approach, we do manage to detect dependencies between different iterations, regardless of the type of loop. And yeah, depending on if these dependencies are on addresses which haven't, as explained in before, the dependence finding algorithm. If the addresses are not, let's say,
Statically identified.
yes.
So for addresses which are not statically identifiable, then we use the dynamic analysis part.
Yeah, and which ones are statically identifiable depends on whether they are passed to other functions or accessed by pointers.
Exactly.
Yeah, thank you very much. I guess I was most interested in not just detecting dependencies, but understanding the dependencies in terms of some kind of dependence distance vector with respect to the enclosing loop nest, for example.
I see. So actually, we use the chain analysis and the control flow graph. So in combination of these two, so these are the methods that we use to get the static analysis. So in our previous work, we used the Pluto, which used these affine loops with affine bounds. So and we got the data dependencies with Pluto. But with the current work, we consider the use of chain analysis and in combination with the control flow graph. So if we detect statically that we can identify the addresses of variable statically, then we mark it for static dependence analysis. Otherwise, we leave it for the dynamic analysis.
Thank you very much indeed.
Thank you too for your question.
Okay, so great discussion, but I have to stop you there because we have to. I hope that it answers fully the question, but we have to move on. So thank you again for the presentation and for the question and for the answers. Let us move to the second presentation of this session, and this will be about a toolchain to verify the parallelization of OMPSS2 applications. So let us...
Hi, my name is Simone Conmo. I am a PhD graduate in computer engineering at Sapienza Università di Roma. And in this presentation, I will talk about the research work that I have done in collaboration with the Barcelona Supercomputing Center on a toolchain to detect parallelization errors in OMPS2 applications. Parallel programming models can leverage the capabilities of modern multi-core architectures and can support the concurrent organization of work inside HPC applications, thus improving their execution time by orders of magnitude compared to sequential execution. In this presentation, we focus on task-based models, where execution can be represented by a direct acyclic graph. Nodes are tasks, and edges are ordering constraints between them. This structure establishes a partial order so that tasks that are not reciprocally ordered are free to run in parallel. To ease the burden put on the user to parallelize applications, the annotation-based approach has arisen. Starting from the sequential version of the application, the user can incrementally add more and more compiler-based annotations to specify the parallelism of different parts of the application. Despite that, the parallelization process remains manual and prone to a variety of errors. Spotting these errors is a very time-consuming activity that can lead to many hours of debugging. Parallelization errors are errors belonging to the parallelized version of a program. They can be roughly divided into correctness errors, when there is a lack of synchronization that alters the original sequential program semantics, and performance errors, when there is an excess of synchronization that slows down the application unnecessarily. Usually, detecting these errors requires algorithms that are tailored to a specific class of bugs, especially correctness ones, like data races. In our work, we are interested in detecting and reporting another class of errors called compliance errors, which can be the cause of several correctness or performance bugs. They result from not respecting the rules of the programming model being adopted for the parallelization. Their presence can be detected programmatically if the rules of the model are well defined, as we are about to see for the OMS2 model. For the sake of completeness, we also mention domain errors. These are errors which happen when the user doesn't understand how to arrange code in tasks and how they depend on each other, despite respecting the rules of the model. While domain errors too can be the cause of correctness and performance bugs, detecting these errors in general requires a knowledge that only the user can possess or that is inherently bound to a domain-specific abstraction. We now proceed by explaining the OMS2 model and its rules, by also introducing the compliance errors associated to it. Everything in OMS2 is a task, including the main entry point of a program, named T0 in the example. If a task is a child of another task, then it will execute after the parent has started executing. This is represented by a started dependency in the example. Each task can also specify a dataset, an annotation which describes the accesses that are performed by a task during execution. If two tasks access the same variable and at least one access is a write, the task that was created last can't execute until the other has released its variables. This is represented by the in-B and in-out-D data dependencies in the graph. Unless stated otherwise, tasks automatically release their variables upon completion, but the explicit release of a data dependency in the middle of a task is also supported. Notice that this example contains two compliance errors. T1 and T2 both access A, T2 writes to it. However, T1 doesn't declare this access in its dataset. Strictly speaking, there is a missing out A constraint dotted edge in the picture that might cause a lack of synchronization, hence a correctness bug, between T1 and T2. These errors are called E1 errors. Also, T2 declares to read-write D, which is not true. This creates unnecessary synchronization between T2 and T3, a performance bug, represented as a red edge in-out D in the picture. These errors are called E2 errors. Generally speaking, execution order constraints coming from matching task datasets can only be established between sibling tasks. If two tasks are in siblings, even if there are neither E1 nor E2 errors, they won't be able to form a dependency. To fix this problem, OMS2 has weak datasets. The model states that every time a task declares an access in its dataset, that same access must be declared in its parent in a weak form. By means of this annotation, the parent task acts as a bridge between its children and its siblings, thus allowing the two sets of tasks to form dependencies, if any. For example, T1 is used as a bridge to help T2 and T3 establish a dependency on B, out B in the example. However, notice that the weak access in T1 doesn't prevent T1 itself from executing in parallel with another task accessing B, since T1 is not really accessing that variable. This example, just like the other, contains two compliance errors. First, T1 doesn't declare a weak access on C, thus failing to bridge T2 with any other task which may access it. In the example, T2 and T3 should form an out C dependency, dotted edge in the picture. Indeed, if the out B dependency is released before T2 completes, T3 might race with T2 on C. These errors are called E3 errors. Second, T3 declares a weak access on D, but no child task writes it. While this error doesn't necessarily produce a correctness error or a performance error, it might suggest the presence of such errors elsewhere in the program. These errors are called E4 errors. OMS2 also has barrier synchronization. A task wait is a construct that lets the task wait until its children have terminated. The set of children on which to wait depends on the dataset specified in the task wait itself. In the example, the first assertion is only executed after all children that have written X have terminated. Therefore, T1 can be conceptually split into two parts, A and B. The first part is responsible for spawning T2 and T3. The second part executes the two assertions. Notice, however, that while T1b correctly waits for T2 to release its writing on X, it doesn't wait for T3 to do the same on Y. The two tasks will therefore race on this variable, thus potentially generating a correctness error. These errors are called E5 errors. Our automatic detection analysis exploits the rules of OMS2 to verify the compliance of each task by means of an analysis which we call local task analysis, or LTA. It checks that a single task is free of the compliance errors previously introduced. It is called local because, to detect compliance errors, it only needs information local or relative to that task. In particular, given a task to check, E1 and E2 can be detected by matching its accesses with its own dataset. E3 can be detected by matching its dataset with that of its parent, and E4 with that of its children. E5 can be detected by matching its accesses with the dataset of its children. Contrary to other non-local algorithms, we don't need to involve other tasks in the program, for example, sibling tasks, and we don't compare directly accesses from a task with accesses from other tasks. Because of this, we can analyze each task independently, even in parallel. Our approach allows extending LTA to the whole application. Remember that in OMS2, everything is a task, and every task can spawn other tasks internally. Since LTA detects compliance at the level of tasks, it is possible to use structural induction to prove the compliance of the task representing the main entry point of the program. More specifically, according to our definition of OMS2 compliance, we can compose the local task analysis carried out on each task to prove the compliance of increasingly bigger regions until we reach the main task. If that task is compliant, then the whole application is. Our toolchain is hybrid and divided into a compile time tool and a runtime tool. The compile time tool executes static LTA on task declarations in the source code. It can detect errors which are independent of the program input and doesn't produce any overhead at runtime. However, it cannot analyze code that is not available during compilation, for example, shared libraries, and when lacking vital information about the program to continue its analysis, it doesn't say anything about compliance. The runtime tool, on the other hand, executes dynamic LTA on task instances in the binary code. It can access all code that is executed and all information about the program at runtime, so it has better coverage than the compile time tool. However, it is also way more intrusive and only detects errors that happen with the tested input. To bridge the gap between the two tools and improve the overall detection accuracy and overhead, we introduce some additional annotations called verification annotations, which we explain in the next slide. Verification annotations have two purposes. One is to disable instrumentation inside the annotated regions to reduce the overhead of analysis, especially when calling functions doing heavyweight computation or running synchronization code. The other is to save the accesses in the annotated region that are still relevant for analysis, as a way to avoid reducing the accuracy of LTA while disabling instrumentation. The lint annotation works on arbitrary code. It accepts a dataset that is useful to describe the high-level semantics of complex library functions, such as reading or writing buffers in MPI send or receive functions, or also to reduce the number of accesses to instrument using a more compact representation for them, for example, when traversing an entire array. The verified annotation is used to document the compliance of tasks and the validity of their datasets. It is also extremely useful to support incremental detection scenarios, where the user wants to focus analysis on a subset of the task declarations or instances. Indeed, it accepts an optional Boolean expression to mark as compliant a subset of task instances, which are those for which the expression is true. Overall, our hybrid toolchain works as follows. The compile time tool accepts as input the original source code, possibly annotated with manually placed verification annotations by the user. Detected errors on the remaining parts are reported at the end of this pass. The compile time tool will also try to place additional verification annotations in code, this time automatically and leveraging on existing manual annotations. Next in the chain is the runtime tool. It accepts as input the final program executable, which may have the manual verification annotations placed by the user and the automatic verification annotations placed by the compile time tool. It can also be invoked without the compile time tool, hence without automatic annotations, or without manual annotations. Detected errors on the remaining parts are to reported at the end of this pass. In this slide, we show the outcome of our experimental analysis of the overhead of our technique. We test some representative benchmarks with and without manual and automatic annotations by measuring the time to run dynamic LTA on the instrumented program compared to an instrumented baseline. On the y-axis is the slowdown relative to such baseline, while on top of each bar we show the absolute execution time in seconds. As we can see, instrumentation and runtime analysis alone can be expensive. The Cholesky experiment was still running after hours of execution. However, in all the other cases, the absolute execution time of these experiments was in the order of minutes. Notice that we tested our benchmarks with small input sizes, as these sizes were representative of the execution of benchmarks even for larger inputs. If production-level inputs must be tested, it is possible to use verification annotations to selectively instrument those parts triggered by such large inputs. When using verification annotations and the compile time tool, the scenario is much more favorable. Lint and autolint are very effective on benchmarks that spend most of their time inside external code. For example, not only Cholesky terminates this time, but also very quickly, since it makes heavy use of the annotated Intel MKL libraries. Benefits are also evident for communication-intensive benchmarks using blocking MPI calls protected by manual annotations, like nbody and heat, or benchmarks which make use of execution kernels with very predictable loops that the compiler can understand and wrap inside automatic annotations, as for example matpul, .product, and multisaxp. In all other cases, the net effect can be almost null, like HPCCG and merge sort, or it might be slightly negative, as for example nqueens, due to the cost of processing such annotations at runtime. Overall, this suggests that the locality and composability of our analysis, together with the hybrid architecture we use that heavily relies on verification annotations, is effective to detect compliance errors in OMS2 applications in terms of detection overhead. An experimental analysis of the accuracy of our technique is out of the scope of this work and will be the subject of future research. This concludes our presentation. If you got any doubts or simply want to know more about it, feel free to write to us or ask a question during the live session. Thank you for watching.
Yes, thank you for the presentation. And now we have some time for questions. So please use the Slack channel to ask them. You can always also raise your hand in Zoom to be promoted to panelist and ask the question directly if you wish to do so. Well, okay then. So since we barely fit in time, and it is right about time for the next presentation. Oh, Paul is writing again. Okay. Yes. Okay, Paul doesn't have this time. So thanks again for providing this talk.
Thank you.